right, so it's my pleasure to introduce Piyush Mehrotra, who's the division chief over at the NASA Advanced Supercomputing Division, where he oversees the full range of high-performance computing services for NASA's primary supercomputing center. And he also manages the modeling and simulation research and development efforts, which are critical for the numerous agencies' missions. Piyush, welcome. Thank you for joining us. We're very excited to have you.
Thank you. Thank you for the invitation. Sorry for the technical difficulties. Zoom is not an application that is traditionally allowed by NASA, so I had to work around that. So what I'm going to try and give you is a sense of how HPC is aiding or sort of NASA's missions. And so let me just jump directly into that. The NASA strategic plan is organized around 4 themes with the vision of exploring the secrets of the universe for the benefit of all. And the 4 strategic goals or the themes are discover, which is expand human knowledge through scientific discoveries, new scientific discoveries, and so on and so forth, which actually is divided into 4 pieces or 5 pieces where you're looking on Earth sciences, looking towards space, both as planetary science and astrophysics and solar physics, and then biological sciences also. So that's all part of the scientific discovery process. And then exploration, which is the biggest piece of NASA, where you're trying to extend the human presence all the way to the moon and onto Mars in a sustainable fashion. And then along with that, there's also the development of innovation to drive economic growth, particularly focused on aviation and having eco-friendly aviation and so on. Underlying all this is obviously objective, the strategic goal to optimize the enabling technologies, and high performance computing actually lands in this enabling technologies piece. So what I'm going to show you is what our center does, and then go into certain applications and visualizations to show you how different pieces of the other 3 objectives are being affected by the work that is being done using our center. Please stop me for any questions if you have. So the NASA Ames supercomputing facility that is just located down the road from you guys there in Stanford is NASA's premier supercomputing center. There's another one in Carter, which is slightly smaller in size, focused mainly on earth sciences. Our charter is to support all of NASA's missions. So at any point, we have about 1,600 users with about 600 projects, science and engineering projects, which are spread across all the 4 mission directorates that NASA supports on the science side. So just to give you a sense of our environment, we have multiple computing systems. Some of you may have used this. The Pleiades was our main system until recently. Aiken, that is shown on the right-hand side, has taken over as our biggest system as of actually last week. And I just wanted to point out that Pleiades is a machine which is sitting inside a building at a traditional data center, HPC center. Several years ago, in about 2015, we started experimenting with expansion of our facilities, and we built a prototype which houses Electra in the middle. And this is a modular supercomputing facility where we do build machines within modules. Many advantages. 2 major advantages are just-in-time capital expenditure for the building. So we put in the building, the module as and when we need it. And 2, we can leverage the California great weather that we have to be very much more eco-friendly. So instead of having big, huge chillers and air conditioning units to cool Pleiades in the building, in Electra and Aiken, what we have been doing is using outside air 90% of the time to cool the systems. When it becomes too hot, above 85 degrees, like it was yesterday, then we have fiber curtains where water flows through it. And as the water flows through it, like in an adaptive cooler or a swamp cooler, that cools down the air, which then cools the systems. Aiken has a similar kind of facility, but it's slightly different with a closed water loop, which cools the actual chips. So when we did Electra, at that point, it became successful. So now we have 1 acre pad on which we can start putting modules. And the first module is shown on the right, and it is now completely full. We're going to be adding another module and so on and so forth. So those are our compute systems. Obviously, we have all the support environment, storage of about 50, 60 petabytes, and tape library, which has a capacity of 1 exabyte. And on the right-hand side, I show you a visualization system called the Hyperwall, which is a 128 screen, 250 million pixels that is being used for visualizing all kinds of things. And I can talk about that a little bit more if anybody is interested. So that sort of gives you, and of course, we have some amount of GPUs, other smaller systems and things like that. GPUs are not a big part of our environment because we haven't seen a lot of usage of GPUs at this point. For traditional scientific applications, the use for AI and ML is increasing, and as it increases, we'll add more GPUs to it. So that gives you a sense of the environment that we have. What I'm going to jump into is showing you a sequence of visualizations which give you a sample of the kind of work that is done on our system. So here's the first one. This is for the launch environment. This is work being done by researchers in my division itself, and they have been simulating the launch environment to help design a new one. Just as I think you see on the lower right corner in a circle is a human, a green human, to give you the relative size of the launch environment with respect to human size. So the idea here is that the launch environment that has been traditionally used seems to be inadequate for the new rockets, which are much larger and so generate much higher temperatures and pressures. So this simulation is a computational fluid dynamics simulation that is done to assist the designers. So when they come in with a new design, the CFDers simulated using about 4,000 or 5,000 cores for a couple of weeks to do one of these runs and provide the design envelope for the designers to work in. What you're seeing in this visualization is the temperatures that are being produced, the lighter colors or the higher colors. But along with that temperatures, they also measure the pressure. And the other thing that they look at is the vibroacoustic characteristics of what is happening here, because the noise generated gets reflected up and can affect the rockets as they're just starting to launch. So what you're seeing is the first few 10 to 15 seconds of the launch itself. And this has been going on between the designers, a contractor, which is designing the new launch environment, and the CFDs. They will come back and say, what if we change the design this way? What is the effect on the environment that you have, the vibroacoustics environment that you have? And then the results are sent back to them so that they can validate what is happening and what the design should be. In the later simulations, they have actually introduced water in here also. So along with just what is happening here, they've introduced the water so that the water is used for suppression of the temperature and the noise. So that's what is being done to simulate the launch environment. Another project is the Space Launch System itself, and they are simulating what happens as a solid rocket booster separates. So there are little rocket engines that are initiated to separate the rocket booster from the core stage. And as you can see, that causes turbulence as it is going and affects the boosters as they are separating out. You can, at the bottom, you see the numbers showing how far away the booster cone is from its core stage. And the issue that they're trying to resolve, that as the boosters go away, fly away, they may actually come back and tumble back into the core stage, causing disaster. So they are trying to analyze what happens to the boosters as they separate and make sure that the kind of the separation is carried out in a form that it doesn't danger the core stage. So those are the kind of simulations that are used. This is, again, about 5,000 cores being used for a couple of weeks for each of these simulations. Okay. So this is to support human exploration. This is the Space Launch System with Orion as a crew vehicle on top. There are other things that are being done, launch aboard the system. All kinds of databases are being generated on the design and so on and so forth using our the HPC system. Switching areas, this is a simulation that is done to simulate the global state of the ocean. This is a project called by the ECHO Consortium, estimating the circulating ocean model. And jointly between JPL and MIT and other agencies, what they are doing is they use observational data to as input at the start, and they have a grid on the surface of the Earth, 250 million grid points, where they calculate the pressure, the velocity, and the salinity of the water. What you're seeing here is the velocity of the water. It's the lighter the color, the higher the velocity. They also have 90 grid levels going deep into the ocean at 5 kilometers, all the way to 5 kilometers deep. So what they've been doing is simulating this to figure out how the ocean is changing over time, starting, like I said, with some observational data and maybe correcting it in between. But all this is being done as a simulation. And this is one of the largest applications that have been run on our system, about 90,000 cores, and has produced about 5.5 petabytes of data. What the simulation that you're seeing here, the visualization is showing you some gross effects, how the water is moving across the oceans, and actually can see finer granularity effects. It's a 148-degree grid, so about a kilometer between grid points. In fact, when we show it on the hyperwall, you see all the finer fineries of this. The data that is produced is then used by other scientists to figure out things like ice melting, climate change, debris tracking. The initial work was done just focused on the ocean, but now in the last year or so, they've been coupling it with the atmospheric model, where the scales are very different between the ocean and the atmosphere, and trying to see how the atmosphere, what is happening in the atmosphere affects the ocean, and versus what happens in the ocean, the temperature and the velocity of the currents, how it affects the atmospheric model. So this is looking at sort of Earth and seeing how the global state of the ocean is running. Switching topics again, this is a simulation of the merger of black holes. Two black holes are rotating around each other, and then they merge together, producing gravitational waves, which have specific patterns. And so what we are showing here is a very unique way of doing things. Scientists from the Goddard Space Flight Center built a whole database of these simulations with different rotating spins and different sizes of the black holes. And they built this whole database where they figured out what the patterns of the gravitational waves that occur when the black holes merge with each other. So in 2016, LIGO, one of the gravitational observatories, actually detected a gravitational wave from 1.5 billion light years away. And scientists started examining that. So this group of scientists from Goddard looked at the gravitational wave pattern and determined the size and the spin rate of the black holes that merged, resulting in that gravitational wave. And this visualization that you see right here is using that parameters to see what was happening to the black holes. So this is work being done in astrophysics to figure out how black holes merge, to understand the merging process of black holes. Okay. Switching topics again, like I said, what I'm trying to show you is that the work being done on our systems is affecting all of NASA's missions. So this is affecting the Aerosciences Mission Directorate, where they're looking at how aviation can, doing underlying research in aviation, doing design work in aviation. So at the top left, you see drones, which have become really popular. But the idea is, how do you design the drone such that it is most efficient and causes the least amount of noise? So what you're seeing at the top left is analysis of a quadcopter, where you're showing Q criterion values, basically the turbulent flow that is happening because of the blades. And what they're worried about is the vortex interaction with the blade behind. So the flow that is produced by the blades in front interacts with the flow which is coming off the blade behind, and causes problems with efficiency and the drag that is caused. And in all the design process, they've been looking at different models where they're putting the blades at the back in facing downwards below the copter rather than above the copter. They're also looking, like I said, the noise issue. Most of the noise that is generated by the blades is fairly easy to predict. It requires only very low fidelity tools to do it. But noise that reaches the earth, broadband noise as it's called, which is high frequency, low bandwidth noise, that's much more difficult to predict. So they are developing tools. This is particularly a group in my division, the LAVA group, which has been focusing on using lattice-Boltzmann equations to do the simulations that you see on the top left. On the bottom right, you see looking at aircraft and trying to predict the lift that is generated by the aircraft, which is crucial when they're companies like Boeing and all are designing aircraft, because they need to see what kind of lift will be generated so that they make sure that they don't stall the plane. And what you're seeing is these brackets or the slats are producing the turbulence and the weight that is happening there, including the ones at the juncture of the wing and the fuselage. And these are then used to predict what kind of lift would be generated and what kind of inefficiencies would we have. So this kind of analysis is used to analyze the design of these aircraft. There are all kinds of experimental aircrafts that people are looking at, electric-based aircraft rather than gasoline-based aircraft. And this is the kind of work, mostly in computational fluid dynamics, that is being used to look at different aircraft interfaces. Okay, I'm going to switch a little bit to topics again, and most of the work that I have been talking about up to now is large-scale simulations and physics-based modeling and simulation, and work that is being done in the different era. And in the next two slides, I'm going to show you what is called, sometimes called urgent computing, sometimes called near real-time computing, where in this case, this is a prototype that was done about 1.5 years ago, where we connected the wind tunnel to the HPC system. So generally how this was done is this is a model of a SLS that's running in a wind tunnel, using pressure-sensitive paint. And as air flows around it, the pressure on the fuselage and on the changes, and the paint changes color based on the pressure level. And video cameras actually then capture the changes in pressure, and this is then analyzed to figure out what is happening on the surface of the craft. Now, the traditional way was to run these experiments in the wind tunnel and then dump the data. The data goes back to the engineers, and it takes a few months before the engineers could, reformat it and use it and see it and analyze it. So what we did was connected the wind tunnel directly to the HPC system, and the analysis that took 24 hours on a workstation, we speeded it up so that each frame, a set of frames that came through were analyzed on the machine in a few minutes, in 5 minutes or so. And so this kind of data was available to the experimentalists almost immediately. Now in the prototype, they actually came back in the evening after running the experiment during the day, came back and looked at what the results they got, something that they could not have done for months after the experiment, but they came to our building to see what had happened. The larger vision is that this will be connected directly, and the engineers could see what is happening in near real time within a few minutes of the experiment actually being run, and so that they could make some corrections to the cameras and to how the next set of the experiments will be done. So you start getting, in fact, to get into computer-guided data acquisition. Another real time, which is sort of different than the sort of edge computing that I was talking about in the last slide, is analysis of observational data. Urgent computing or near real-time computing of the observational data. Traditionally, the satellite observational data was in polar orbits or equatorial orbits. Was the satellite would go over a piece of land once a day, or so the temporal frequency of the data was hours, 24 hours, 48 hours, and so on and so forth. In last few years, NOAA has been sending up what are called geostationary satellites. So these are satellites which are hanging at the same spot relative to the Earth, and are producing data with a cadence of about a few minutes, 1 to 5 minutes, rather than several hours. And what that does is it allows the scientists or the folks to look at and figure out what is happening now on the surface of the Earth. And this is used for all kinds of things like irrigation and surface temperatures and so on and so forth. What I'm showing here are a couple of projects that were done by these data coming from these satellites. We call the GOES 16 and 17. They're two satellites that cover most of United States, or all of United States, with a little bit of overlap between them. But this is focused only on California. On the left-hand side is visual images of the fire, Woodsley Fire, and the Camp Fire up in the north. In looking at what is happening there, the idea is to be able to provide information to the firefighters as to what is the effect of the fire, where is the smoke flowing, and things like that. On the right-hand side is data coming from a geostationary light mapper. So this is lightning bolts, and analyzing the data as it comes down, extracting the lightning from there, and figuring out how that is affecting the wildfire that is happening, and providing that information once the whole system is built back to the firefighters so that they can understand where what is the lightning and how that is affecting how the wildfires are progressing. So this is sort of near real-time processing of the data that is coming down and using for disasters such as wildfires. So what I've told you, given you a spectrum of sort of either physics-based modeling or with near real-time data. I just want to touch on sample AI/ML projects. NASA was in some sense late to the game, but in the last 18 months, there's been an explosion of projects using machine learning, deep learning for various aspects. I'm not going to go through any of these projects, but just give you a sampling of it. Feature detection, shock waves and vortices from flow data. TESS and Kepler are projects that have been looking at stars and trying to figure out exoplanet, particularly Earth-like exoplanet. So looking at that data and identifying that, artifact identification from satellite data, such as irrigated lands, trees, and so on and so forth. Those kind of things. Prediction, solar flare prediction, space weather prediction, asteroid properties, so on and so forth. Anomaly detection has been used very successfully in looking at safety, aviation safety issues from flight data that could possibly affect the safety of aircraft. The systems behavior, ISS control operation, so on and so forth. There's a lot of work that has been done that uses machine learning. One of the things that just started about 6 months ago is looking at machine learning emulators for physics-based models. So you've got physics-based, CFD-based models. Can we run machine learning applications which can mimic what the model would predict? So that's a project, about 3 or 4 grants that have been given. And this is all on the science side. On the mission support side also, there's work being done in all kinds of scientific document tracking, network traffic anomaly detection, and so on and so forth. So there's a bunch of these applications that are being looked at, and a lot of them are being done on our system, but also on the cloud, as just like Addison was just saying before. I gave you a sense of what we are achieving. I did want to touch upon a little bit of what our challenges are in some sense. So here's a survey that was done about a year and a half ago by several of our users to get a landscape of what their usage was. And as you can see on the left-hand side is what are the programming languages that they're using. And even though C, C++, and Python and so on and so forth are increasing, a fairly significant amount is still Fortran, which is, 5 or 8 years ago, this was up at the 80% level. So now we'll be down to 40%. There's an increase in C and C++ and Python, high-level languages like that. Obviously, a lot of use of libraries, because a lot of this are scientific computations which require PETC or BLAS and things like that. The codes themselves are mostly either in-house codes that have been developed within NASA, or open source codes. The use of commercial software is fairly limited in our environment. We don't have too many people using ANSYS or things like that. There is commercial software for things like visualization and things like that. But scientific software is more either developed in-house within NASA, or it's an open source code that is used by scientists and engineers all over the world. So that gives you a sort of a landscape of what the usage is like. In terms of parallelism, if you look at on the left-hand side, you can see most of our uses MPI or MPI plus OpenMP. Okay, there's a little bit of pure OpenMP, where very little of it. Then there's some amount of CUDA and pthreads and things like that. But mostly it is MPI and OpenMP that we have. And if you look at what kind of packagings there is almost 90% is just pure parallel, but there is some usage of what we call serial packaged together to run across multiple nodes. So this is like when you're running databases of a parameter space study, and each of the code itself is a single core or a small set of cores, but then you have thousands and thousands of it. So the total usage is still large, but instead of it being one big, huge parallel system, it is more of a set of small job executions. And there are various ways that people are using it, either PBS job array or no parallel. So why I was also telling you is that that leads to some programming challenges that we have for our environment. Just like Addison was just telling us that, target architectures are becoming very complex, not only because of accelerators like GPUs, DPUs, vector engines, but within the CPU, within the traditional, also your increasing number of cores, deep memory hierarchies, complex IO infrastructure, all of these are causing problems in terms of efficiently using the underlying system. And then on the other hand, there is a multitude of programming models and languages. Like I said, people are using C, C++, Fortran, OpenMP, and then multiple levels of parallelism. How do you exploit that? How do you do offloading for accelerators, OpenACC, OpenCL, all kinds of one API, I think Addison gave a pretty good landscape of the different approaches for accelerators. And then, so people are using these scripting languages like Python. Julia is seeing a fairly rapid increase. Cocos is also a multi-target environment. And there's some work on domain-specific languages, with frameworks which allow a particular domain code to be written at a much higher level. So the target is complex, the approaches are difficult, and users want both code and performance both. So they not only they want to be able to go from one architecture to the other without making much changes, but they want the best performance in each one of them. And that's one of the reasons, for example, CUDA has not been that successful, because it doesn't lead to code portability. You can get the best performance out of a GPU, but being able to take that and now run it on something else is very difficult. So that's the requirement for the use. From NASA, what we see is that we have large legacy code bases. We have codes that were written 30, 40 years ago with 100,000, 200,000 lines of code. How do you now refactor it, optimize it such that you can then utilize these new architectures in the most efficient way? You can do a major rewrite, or maybe to try and use these architectures. And in fact, as these new architectures come in, maybe you want to actually change your algorithms to a more appropriate algorithm, which is more suitable, for example, for a vector engine than for a system without vector. And underlying all of this is the fact that there is a lack of budget, at least at NASA, for tackling this problem. A lot of the budget goes to the science side, and as long as they're getting some level of performance, there is no budget left for improving the performance of the codes, improving the portability of the codes. It's a fair amount of effort that is required. One code out of NASA Langley, porting it on GPU, they did it very successfully, but required, I would suspect, about 10 person-years worth of work to take that code and run it on efficiently on GPU. And that required a fair amount of resources. The other thing that we are seeing is a lack of expert labor. The expertise is not there. People are going towards, data analysis and data science, and everybody is running there. not very many people are coming towards HPC. And this is both on the domain side and also on the computer science side. So both of those sides, it's difficult to find people who have expertise knowledge of these areas. And as the other areas like machine learning and are increasing, all the folks that are coming out of graduate schools and undergraduate schools are attracted towards that. It's very difficult to attract them to come into work in our areas. These are the challenges. Some of the ways that we are trying to get around it is by, for example, having hackathons. By having hackathons, at least the scientists who are interested, we give them an opportunity to understand what a GPU could do, how to utilize a GPU, and maybe have them build mini apps that could then be ported to GPUs before they actually tackle the whole code and figure out how to optimize that whole code. The other thing that we're trying to do is set up co-design teams. So we're trying to match domain scientists with computational scientists and computer scientists to try and see if they focus on a code, they look at it, they analyze it, where are the bottlenecks, and then try and come up with a strategy of what is the best way to optimize that code. Do we rewrite the whole code? Do we take pieces of it and refactor it and rewrite it in a different language? And then try and implement it based on the target architectures and the domain that they're working. So I've given you a sense of what the systems are being used for. Bottom line takeaway, there's enough computational power so that you can get the kind of granularity, the fidelity of the codes to help us look at all the aspects that NASA is interested in. I'll stop there and take any questions.
Thank you, Piyush.
Thank you. Thank you for giving me this opportunity.
Sure. Absolutely. Thank you, Piyush. I don't have any questions in the queue, but we really appreciate the presentation. Thank you so much.